when we divide rational expressions, it's not much more difficult than multiplying rationals. There's just one extra step. And if we think about fractions, we know how to go ahead and multiply and divide fractions. We just apply that here. First thing I want to do, though, is look at what I really have in example 1. Remember how we can change that division sign into a fraction? So technically what I have here is this really nasty compound fraction, where I have the first piece, which is a fraction itself, and it's all divided by the second piece. So this is what I'm really simplifying right here, is this horrible mess of the one rational polynomial divided by another. So we write it with, again, this symbol right here, the divided by symbol, because it just makes it a little bit easier to deal with. So if we remember, whenever I divide fractions, what I really do is multiply by the reciprocal of the second fraction. So I'm going to change this to multiplication. We take the 3n plus 6 over n squared minus 81. And then we just keep the first part the way it was, the first fraction. So that's n squared plus 19n plus 90. Some places teach it as keep, change, flip. Keep the first one, change the sign, flip the second. So you're multiplying by the reciprocal of the second. And now we're just down to what we did before as multiplying rationals. So I look at my types of factoring. So here I have GCF in the upper right, difference of squares in the lower right. I have A is 1 in the upper left, and I have GCF in the lower left. We have to be able to identify those fairly quickly. So let me keep track of my steps up here. First step I did was change to multiplication, MTP, how I abbreviate it. Second step is I'm going to factor. I'm just following the same steps now that I did before. So multiplication, then factor. So if I look at my factored form, I'm just going to give these to you. You can figure them out. I have n plus 9, n plus 10. I got those using a equals 1. I have GCF of 3 and n plus 10. And then multiplied by GCF of 3, n plus 2. And difference of squares becomes conjugates, n minus 9, n plus 9. So I have multiplied, change it to multiplication. I have factored. And the next step, before we reduce, we have to find the domain restrictions. Domain restrictions, and this is where it gets a little bit tricky. Because remember, domain restrictions come from denominators. So look back over here for a second at this side. If I look at who has ever been a denominator, it's pretty clear that the 3n plus 30 has been a denominator. So I'm going to have to get domain restrictions from there. And obviously, 3n plus 6 is a denominator. So I'm going to have to get domain restrictions from there. And n squared minus 81 has been a denominator because he's in the denominator or the bottom of that fraction. And here, obviously, he is a denominator. So I have to get domain restrictions from there. So there's 3 pieces. That's the tricky part. 3 pieces to get your domain restrictions from. So when I list those out to the side, like I normally do, my domain restrictions are going to be n does not equal. It's going to be negative 10. I have plus or minus 9 and negative 2. And we found a lot of domain restrictions, so this should be pretty typical. The tricky part here is just figuring out where they come from. I'm looking at 3 places, not just 2 places. My final step when I'm solving these then is to reduce. Remember, we reduce binomials with binomials and monomials with monomials. So n plus 10 and n plus 10 go. Since I'm multiplying, they're all on the same fraction, so I can reduce the whole way across. And the monomial of 3 and 3 is going to reduce out. So my final answer, if I write it over here, I have an n plus 2 left on the top, and I have an n minus 9 left on the bottom. So there's 2 pieces to my answer, the rational polynomial and the domain restrictions. Just be careful when you're dividing because there were these 3 places that I have to find domain restrictions from.